Great, thanks, Will. Don't clap yet. You haven't heard what I have to say. No, I appreciate you guys showing up and taking a little time with us today. As Will mentioned, we're going to talk about ICF, but if you're familiar with ICF, you might not have seen something that looks like this before. This is composite ICF. So this is what we feel is a more efficient, cost-wise, more sustainable, easier to construct type of insulating concrete formwork. And I'll go into detail on that. At a higher level, our product or composite ICF in general is really a marriage between concrete block, concrete masonry, and ICF. So we've taken the cost and constructability of concrete block and put that together with the energy efficiency of ICF. You know, we've got some other products here that Mr. Morton's going to talk about later, and you can see the similarity between concrete block and some of these alternative building products. Because it's an easier way to build, you can utilize the skills that the trades already have and already know. You're not retraining these guys from square one. So that's important. We'll have a chance for questions at the end, and then we're building a wall outside. Y'all probably saw when you were on your way in. So we'll stick around that wall as long as you want. We'll build it, and we can pour concrete if you want to, but it might be hard to get it out of there at that point. We are live tweeting this session, and it's going to be on YouTube as well, on our YouTube channel at Bautex Systems. So if you hear something interesting or you want to talk to a colleague about it and they're not able to attend, they can go watch this on YouTube very shortly. This is an AIA course. You're going to get an hour-and-a-half credit if you need the AIA credit. If not, we can send you a certificate as well if you've got a PE requirement or another Texas Board of Architecture requirement. We'll send you out certificates. The one who'll do that is Tiffany Garner. Wave in the back. Tiffany, there she is, hiding in the back. She's our rep here in Austin, so some of y'all may know her. So these are some of the things we're going to talk about today, but Will's pretty much already gone over that. We're going to try to conserve time so we can talk about enough of this and get you out of here in time. So the drive to more energy efficient wall systems is really being driven now by the code. So some of those code changes, when you get up to the 2012 version of the I codes, so 2009 and before and 2012 and after, I look at it as two different sections. Continuous insulation is part of that code requirement, and I'll talk a little bit about that. Some instances there's more insulation required. The continuous component is to eliminate thermal bridges through the wall, so to eliminate an easy path for energy to flow in and out of your structure through something that's not insulating material. And that usually takes the place of continuous foam insulating material, and there are many different types and styles of that. Thermal mass is a big part of systems like we'll talk about today. So the heavier the wall system, in general, the better it's going to perform from an energy efficiency standpoint. So mass wall systems per code definition are things like ICF, all types, including the type we'll talk about today, tilt wall designs, concrete masonry designs, and so forth. So mass walls are important, generally more energy efficient, and of course air barriers. I know this group has a lot of air barrier expertise. We'll touch on it a little bit, but continuous air barrier is part of the code. So you've got to meet those air permeance requirements, and you've got to consider that when you design your wall profile. So this is a map taken from the IECC. It shows the different climate regions in the U.S. Of course, here in Austin, we're in Zone 2, but we're right on the edge of Zone 3. And that determines when you go for a prescriptive look, a prescriptive design of your insulation in your wall system, these tables refer to that climate zone. On the left-hand side here, this is taken from the IBC, this blue table. So for commercial construction, for residential construction, we've got the green chart there. But you go to climate zone 2, for example, you've got different framing types: wood frame, metal building, and mass wall systems. And these numbers in that table, of course, are R value. If you've got a CI following that, it's continuous insulation. So that component has to be continuous around the envelope of the building. Mass wall, you can see the R value requirement's quite lower. That goes back to that the fact that thermal mass helps the energy efficiency of that wall system. So, for example, in Zone 2, a mass wall you need an R5.7 continuous. In a metal building, you need almost R20 total, 13 bat or spray foam, 6.5 continuous. So that code really recognizes that energy efficiency difference there. Air tightness, big part of the new codes, 2012 and 2015 codes. 2012 IBC air requirements. This material air permeance, that's what most folks look at when they're designing a wall system. And typically that can be handled in a couple of ways. The IECC code has a table for standard building materials, so you can go see what the air permeance is on a 6-inch solid poured concrete wall, or you can go to the manufacturer of an air and moisture barrier. And there are a lot of good products out there that are combined products that combine air and moisture barriers. They're typically spray applied or trowel applied to the exterior of the structure, no matter what it is, mass wall, exterior sheathing, CMU. So that manufacturer can typically provide those values for you and provide test reports that certify that product is code compliant with air permeance. So some of these increased insulation requirements, the continuous insulation requirement, they could make traditional construction a little more challenging. You may have to design your wall profile differently, adding more insulation or sometimes more expensive insulation, going from an EPS sheet to an XPS product, something like that, can add a little bit of cost, but you get that higher R value. You can have more layers, so you're adding an air barrier layer, you're adding more insulation layer, a continuous insulating layer, can lead to more complex details, can be a little bit more expensive and difficult to construct, and anytime you're adding foam plastic to a wall, insulation in any form, you have to consider the fire issues. So make sure that product's code compliant with regard to fire. There are some different programs out there that are trying to be more sustainable by removing some of the fire retardant from foam, and there's kind of a risk-reward thing there, but you have to make sure it still complies with the fire code. Moisture issues, you can get mold and get moisture penetration there as you add layers. So if you don't have a really good air and moisture barrier around that building, it can affect your moisture resistance and resistance to mold and mildew. I'll talk a little bit about composite ICF now. That's what we're going to build the wall for y'all outside. Again, it's a marriage really between CMU and ICF. These blocks and the blocks that are outside, they're 90% expanded polystyrene foam. So go out, pick one up. They're pretty light. You can pick one up quite easily. These beads, you can see these small beads there. We use what's called an engineered bead that gives you a very regular shape and very consistent dimensions of the product. We'll walk you through. The wall system functions very much like a CMU wall system. It installs very much like a CMU wall. This wall system can provide the structure or a building envelope. So it can be load bearing or non-load bearing. It can provide the fire resistance, which I'll talk about in just a minute, continuous insulation, and your air barrier in a single integrated assembly. So you're qualifying for that continuous insulation requirement of the code. Composite ICF blocks like the one you'll see outside today, those meet up through the 2015 building code requirement for prescriptive insulation in the wall throughout the whole lower 48 states. So you don't have to add foam to this. You don't add insulating material to this. And you get it all in one product. So basically the formwork is there to allow you to build a concrete structure. So at the end of the day with ICF, any kind of ICF, you're building a concrete structure. So anything you can build with concrete, you can build using formwork like this and a few modifications. And we'll show you some of the more common ones outside today. Some of the benefits of composite ICF, you've got, of course, reinforced concrete construction, a very durable construction method, very economical in this part of the country. Concrete's relatively inexpensive. Energy efficiency, that insulation combined with the air barrier and the thermal mass of the product gives you a very energy efficient wall system. Fire resistance is a big part of the product. This block filled with concrete is a 4-hour load-bearing fire-rated assembly. So you can use this in firewall conditions without having to buy a special fire block. without having to re-detail your wall in those firewall areas. You just keep going with the same exterior, and it's already got all the insulation in it. One of my favorite parts of our wall build demo when we go outside is I've got a propane torch. We'll put it right on the wall, and you can see kind of the reaction to direct flame. But from a practical standpoint, it lets you use welded connections. You can weld over top of this wall system without worrying about catching formwork on fire, melting anything, and you're free to use a lot of different connection types, and more products become available to you with regard to that. Sound deadening, this block with common finishes, it has an STC of about 51, which is generally pretty good for a block system without adding any layers to it. Storm safety, composite ICF filled with concrete is an ICC 500 and a FEMA approved hurricane shelter material. And when you add with the addition of a brick veneer, it becomes a FEMA approved tornado shelter material. So you can do community tornado shelters, community storm shelters out of products like this and what you'll see today. Recycled content's a big part of the product. This block is about 28% recycled content. That's what we manufacture in San Marcos. The industry varies up and down a little bit, but right around that range of recycled material. This is a slide I'll go through pretty quickly. This compares kind of a standard CMU wall system. So an 8-inch partially grouted CMU wall system on the right with 2 inches of XPS rigid insulation, wrapping that wall assembly to give it that CI component, or that continuous insulating component around the outside of the building. Both of these are clad with brick veneer. On the left-hand side, of course, is the composite ICF system, which it's stacked, forms a grid system that you'll see a lot more about outside, and we can show you that grid system in more detail. But the composite ICF system, that backup wall weighs about 50 pounds per square foot when it's installed and poured with concrete. This 8-inch partially grouted CMU is about 75 pounds per square foot, so it weighs about 50% more. In certain projects, that can be an issue. We just completed a multi-story dorm project where that was an issue. We were the wall system for the exterior, an envelope system. And the other alternative was CMU they were looking at for infill. And we were able to reduce the weight pretty significantly and lighten up the foundation load, so that's important. The wall assembly on the left, that yields you about an R18 mass wall system. So that's a mass wall R18, which is important to note. The masonry walls in R15, both more than adequate in this climate region, and both very energy efficient. One of the primary differences between these two systems, though, is the time to construct. And you'll see that illustrated outside. The composite ICF system has a larger block and a larger unit. When we stack these up, each one of these block is the equivalent to 3.5 8x16 CMU. And there's no mortar in the system. It's a mortarless system. So we're increasing the size of the unit and we're deleting the mortar joint. So a composite ICF wall system installs in about half the time it takes to put up a comparable 8-inch block wall. So you can cut down time to construct significantly to get that wall finished. If you're using 12-inch block, the time differential is even more dramatic, because 12-inch block has to be laid quite a bit more slowly. This shows the core system that's formed in a composite ICF wall. You'll notice the windows there where we've, in essence, replaced concrete that you'd normally be filling the wall with extra foam, more EPS foam. You get a 6-inch diameter set of cores horizontally and vertically every 16 inches in both directions. They're fully reinforced with rebar. There are a ton of modifications we can make to this system for heavier walls, taller walls. We can add pilasters, ring beams, you name it. I have a whole nother program that we do an hour on just the structural part of this. We can definitely accomplish larger structures, load-bearing structures with this type of system. Again, you're building with concrete. Yes, sir?
How easy for me is it to cut a hole in that? Versus the CMU, I'm just going and taking out blocks.
Yeah.
What do I do here?
That's a great point. Cutting a hole through this is very easy. It's foam. You'll see the block outside. For example, one of the practical applications of how easy it is to cut into this is the electrical and data install with a system like this. Typically, when a composite ICF wall system is installed, they'll go ahead and put the wall up, pour it with concrete, Then they'll come back, use a rotozip tool or a router, and route out space for the conduit and the boxes. You'll adhere that in and then finish the wall over top of that. So a lot of times electricians don't even come in. On our recent project we did, they didn't even start until the wall was completely finished. You are able to penetrate the wall. We have these 10-inch by 10-inch windows in the product, every 16 inches in both directions. So if you have to make a penetration into the building, whether it's 2 days after you built the wall or 25 years after you built the wall, you can come in, we'll literally take a sharpened piece of PVC, they'll cut it in an angle, set it against the wall, hit it with a rubber mallet till it goes through that core, pull it out. You've got a penetration, sleeve it, run your lines through, seal it, and you're done. So pretty easy to do that. You don't have to call the structural engineer and say, hey, can I cut a hole here? Or you don't have to hole saw through 6 inches of concrete or 8 inches of concrete like you might have to do in a tilt wall or an ICF install. Sir, yes. Okay.
I didn't see any chair support for horizontal steel in the block out there.
He's got them.
Okay.
Yeah, they're there. You can see them when they come out. All the horizontal bars go on chairs. They're fully tied.
But they're integral to the block?
No, sir. No, you're using a standard off-the-shelf chair. So that's not part of the block. You set that in the block, set the bar down and tie it. And he's got it, so yeah, in the block itself you won't see him, but when he's building that wall out there, yeah, you'll definitely see him. And we even have a tie wire system that goes inside the wall that allows you to only put the horizontals in while you're stacking the block, and you drop the verticals in when you get to the top of the floor height, so you can get a nice continuous piece of rebar in there. You're not splicing a bunch of bars. And that tie wire system allows you to actually tie those bars from outside the wall. You pull on 2 tabs. We have a plastic system and a steel system, and you can pull on those. He'll demonstrate that when we look at the wall build demo. I'll go through the construction really quick because I know we want to get Neil up here and hear from him. The quick construction method that you'll see here, we're talking about foundation prep. So you have dowels coming out of the foundation. The block's typically set on the slab rather than a brick lug. It can be on a lug if you want to drop it down for any reason, but typically not. We'll stack these bars. You'll start with the corner and lay out that first course. Install the horizontal bars, corner bars. They are up on chairs. No chairs shown in that picture, but it is supported down the run. I think there might be one up there. Anyway, it's at the center of the core. We get the rebar in the right spot. Cut out and block out for your doors and windows. Put window bucking in. Very similar to window and door bucks that you might use in standard ICF installs or sometimes in CMU installations. Stay-in-place wood is very popular. Removable wood's also an option. Steel bucks can be used as well. So there's a lot of options. This is part of that tie wire system that I was talking about. You can hang inside the wall and catch those horizontal vertical bars. Here are some window and door bucks being installed on some projects. This is just a regular hollow metal door frame. You set it, build a block up around it, and pour concrete, and it'll encompass that frame and lock it in place. The same with these wood openings. That's temporary shoring in the middle, and we'll have a window out there in the wall we're going to build for you today. Some of the bracing with composite ICF is a little bit different than ICF bracing. Composite ICF is a heavier product. Our block weighs about 45 pounds. One block weighs 45 pounds. Traditional ICF product, that block weighs about 5 pounds. So it's going to move a lot easier, and you're putting twice as much concrete into that block. So we're using half the amount of concrete, so half the pressure inside the block, and a heavier block helps things with things like blowouts and so forth. This is simply wood bucking. This is about the simplest bracing type that we can use. It's off-the-shelf products from your builder supply house. It's not something that we sell specialty bracing like some other wall systems. You can also use pole bracing like you would with CMU, and things that masons have on hand generally is what we like. Concrete placement's important.
Can you use regular ICF braces?
You could, yeah. If you have regular ICF braces, that'll work just fine. You won't need the adjustability of that because a composite ICF wall, you get it plumb level and straight before you pour it, and then when you pour it, stays in its position. So you don't need the adjustable aspect of it, but yeah, you could absolutely use standard ICF braces as well. Concrete placement's very important. You need to make the mix design correct. It's an ICF mix. It's an 8 to 9 inch slump, 3/8 inch maximum aggregate. Usually pea gravel or river rock's going to flow a little bit better. You might have a little plasticizer in there to get it to flow. We've done projects with design strengths between 2,500 psi and 7,000 psi. We did a hurricane-resistant wall in Galveston on Galveston Island. It had number 7 bars in it and 7,000 psi concrete. So you can get pretty high strengths inside the load-bearing portion of walls like this. Pouring the concrete's important. If we were to build this room out of composite ICF, you'd stack all the block up, get all the rebar in it before you poured any concrete. You'd pour it in 4 to 6 foot lifts moving around the structure. Come back to that next 4 to 6 feet about 30 to 45 minutes after you've poured the first, but vibrating every core as you go. That's a pencil vibrator on a whip. That's typically what our contractors will use to vibrate these walls. They drop it down to the bottom of the core and back out. That gets you good concrete consolidation, removes any air pockets in the wall, ensures that you get that full. Third step to making sure that all that grid gets filled is there's a probe system that we use. You stick the probe through the outside of the wall. As you're going around the walls, it's getting poured. You stick it in. If it comes out, it's got concrete on the end. You know it filled those horizontals. Very quick and easy to check that and get a good fill. About 14 feet in a day right there because the reach of the vibrator. That's really what kind of restricts you. And dropping that vertical bar in the core, one single piece of rebar longer than 14 feet is pretty nasty to handle and get vertical and drop in. So that's about the break of it. And we'll typically divide that up in floor heights if we can. But we've designed walls up to 40 feet tall. We'll just break it up into different pours. We'll put a ring beam in the middle where we design the pour to stop and start with continuous bars, and then we'll set up and go up from there. And there are ways to do that while leaving the insulation intact on both sides of that wall. So you're just creating a bigger core in the center, carving out from the standard block and allowing that to fill up and give you a good beam to start from. Yeah.
So I noticed your graphics and your images show all of the blocks in a stack coursing or bond.
Right.
Can you talk about that?
Yeah, absolutely. We'll jump up here and show you. Yeah, with our system, okay, we find the contractors prefer a stack bond, and the reason we don't have a problem with it is because the adhesive that we use to hold the block together is actually stronger than the block itself. So in masonry, you generally want to avoid that type of structure. I built with masonry and sold masonry for about 10 years before I was here, and you want to avoid that type of bond pattern if you can, because you're lining up all the weak points. There, the mortar joint's the weak point. Here, the joint is actually the strong point of that. Adhesive actually marries those two blocks together. And you'll see today, after we get done building the wall, if you stick around and watch us tear it down, we have to actually cut that apart with a chainsaw to get it apart and back in the truck. And that's after maybe like 20 minutes. It'll be fully locked together.
So would it be wrong to do like a common bond?
No.
And is there any structural difference between the two in your product?
There's no structural difference, and you can absolutely do like a half bond. You'll create the same grid in the block, whether you do a half bond, a stack bond, or a soldier course. So there are reasons, detailing reasons usually at the top of a wall. We're going to have a floor and roof connection. Why we usually turn the last course into a soldier course. You create the same grid inside, but what it allows you to do is cut out more of the center, and you can get an 18-inch deep ring beam for floor attachments at that point without losing your insulation on either side. So there are a lot of construction details why you would want to vary that up, but this is the most common. Any other questions before I hand it over to Neil? Oh yeah, go ahead.
On the horizontal long axis, expansion
Yes.
joints and cold joints when you're doing your pour.
Yeah, you've got to design, we'll design in construction joints at what we feel are, reasonable spacings. We found we can do a 14-foot plate height. We can do about 400 lineal feet of wall in a day pretty securely. So we'll divide the wall up in that section. As far as construction joints, anywhere where there's one in the slab, you need one in this wall. It's a monolithic pour of concrete, much like a slab is, so you can space those accordingly. And you use the same detailing and the same joint products that you would with it for an 8-inch CMU. Same kind of design details. And we'll have a Q&A session at the end. We can get to some more, and I can let Neil come up here and talk to you for a little bit.